Okay, everybody, welcome. It's good to have you here, and my pleasure to introduce Jeff Bilmes, professor in the W department and also adjunct in computer science and
Okay, thanks very much, Dan. So, hi everyone. So, this is a talk that I think will be of interest to some of you, I hope, and maybe some of you won't find it interesting at all. But if you don't find it interesting, then please don't tell me. So, this is a talk about submodularity, and in particular, it's a talk about the applications of submodularity in machine learning and artificial intelligence. Now, actually, there's a lot of, I should say at the outset, there's a lot of mathematical depth and richness to submodularity and submodular functions in general in optimization. I won't be talking about most of that. But if it is the case that you are the small fraction of people here who actually like what you hear, I'd like to advertise that I will be teaching a class starting in spring on submodular optimizations and applications to machine learning that will go into a lot more of the technical depth behind and the mathematics behind submodularity, and there is quite a bit of it. So, but today's is just basically trying to get an idea of what it is and how it's useful and how it's different than some of the existing paradigms in machine learning. So here's an outline, and we'll be coming back to this outline every so often, and we'll be starting with the introduction. So first of all, I just want to start a little bit with my belief about machine learning and artificial intelligence. And this goes back, I think, to the 1950s and 60s and 70s when people were trying to build computational systems that acted intelligently by using a large number of explicit rules. And around that time, I think people started to realize that maybe humans aren't intelligent enough to actually write programs directly that can act intelligently. And so from that perspective, you can think of machine learning. Machine learning is essentially the study and the science based on an acknowledgement that humans perhaps aren't intelligent enough to directly write programs that act intelligently. And from that perspective, the question is, well, okay, given that machine learning can do things that we're not smart enough to write programs directly to solve, what are some of the sort of grand challenge problems that we might want to address with techniques in machine learning and artificial intelligence? And my personal favorites are a lot of problems that exist today with education, using machine learning to, say, help educate people better or to solve large, massive problems and worldwide problems in poverty and energy and climate change and perhaps health. So these are the kinds of things that maybe machine learning seems promising to try to address that otherwise, without the use of this level of indirection, we wouldn't be able to solve. Now, the question is, what are some of the paradigms, or what are sort of the sub-areas within machine learning that are ideal or that we should be concentrating on? And I was thinking that what is the ideal machine learning method would be one that's, on the one hand, simple to define, and that is naturally suited to many problems, that it's not sort of very specialized, and that it's mathematically rich, and then also scalable to large problem instances. So before we begin, let's do a brief survey of some of the existing methods that perhaps satisfy these four properties: simple, applicable, widely applicable, mathematically rich, and scalable. And of course, the first one that probably comes to most of your minds is convexity. Convexity is an area of mathematics that has been studied, convex optimization, convex functions, and that has been studied for a long time. And there are many books written about convexity and many applications of convexity and convex analysis in machine learning and artificial intelligence. But convexity has some limitations, and that it isn't immediately naturally applicable to a lot of problems that you find in machine learning and artificial intelligence. And in particular, it's not really applicable to discrete problems, or not directly applicable to discrete problems. And that includes problems like active learning and label selection and maybe diverse k-best inference and discrete probabilistic inference. The whole area of machine learning, which is maybe called data science. Well, a large part of data science might be sort of dealing and managing data. Essentially, that the data are basically discrete items. And the question is, how do you sub-select data that's representative of the whole, or how do you partition data so that it naturally applies to a parallel machine? All of those sorts of things really aren't really well addressed by convexity. Not to mention certain sparse modeling methods. I mean, of course, there's convex relaxation methods, but you have to do a relaxation. And if you do a convex relaxation for sparse modeling, then you have to deal with additional potential approximation gaps that might be difficult, if at all possible, to actually find. And then there's other problems in graphical models, like learning structures. And then not to mention, there are many problems in some of the applications of machine learning, like in natural language processing. Language consists of words and phrases and sentences and paragraphs and n-grams and trees and graphs and semantic structures, all of which are discrete. And there's also in game theory and voting theory, there's social choice, choosing a representative population, say for doing a poll. Or in biomedical problems, the question of how do you choose a subselection of the population that's guaranteed to represent the whole population for, say, randomized drug trials in a way that gives you guarantees better than, say, random sampling. So all of those problems are ones that convexity isn't really well suited for. But on the other hand, convexity satisfies these four properties, I would argue. Now, another very prominent example of a machine learning paradigm that satisfies these four properties is graphical models. So let's very briefly define what a graphical model is. I mean, a very generic form of graphical models would be the fact that you've got some graph, maybe it's an undirected graph, and a graph can be described by its set of cliques. Cliques are essentially the set of variables that are fully connected in the graph. And basically, a graphical model describes a family of functions that can be represented by sums of terms, each of which is a function that operates only on the variables that lie within the clique, the corresponding clique. So here, maybe you've got a set of cliques. Let's zoom in on this a bit. You've got a set of cliques B, script B, and then B is one of the cliques. And you have a term, each term of which involves variables only within the clique. And the idea is that within the clique, the function can be unrestricted. But between cliques, you have to have this decomposition property. It's decomposable over the cliques within a graph. So that's what a graphical model is. And you can use this, for example, to define probability distributions, or use it to define constraint satisfaction problems or SAT problems or other sorts of things, all of which are things that are well described by a graph. So here's an example. Let's say that you take three objects, and you're interested in the value of the presence or absence of these three objects, which might be maybe a cup of coffee, a cup of tea, and some lemon. And let's say that you were considering using this graph to describe the value of the presence or absence of any of these three objects, coffee, tea, or lemon. And so we have a value function. The idea is that C, T, and L might be binary variables, and you care about the value of the presence or absence of these three items. And the graphical model says that you are allowed, at most, to have this be represented as a sum of two terms. The first term gives you the value, say, of coffee and tea, or some combination of coffee and tea. And the second term gives you some value, which is T of lemon together. So this is it. Basically, this is what a graphical model, this is what this graphical model allows you to do. Okay. Now, how is this limiting? So here's our graphical model again. Here are three objects, and here's our value function, our candidate value function. The problem with graphical models is the following, that if you consider, for example, coffee and tea together, the value function is really maybe what could be called substitutive, in the sense of the following, that if you consider the value of coffee and tea together, that should be less than the value of coffee and the value of tea. The reason being that if you've just drunk a cup of coffee, you're probably you don't care that much about having a cup of tea right afterwards. And vice versa as well. Once you've had tea, the value of coffee is diminished, and so therefore the value of them both together is probably less than the sum of the individual values. So they have this sort of substitutive property. One can act in some sense as a substitute for the other. But on the other hand, so that basically corresponds to a property of this particular term within the graphical model decomposition of these three items. But on the other hand, if you take the other two objects, tea and lemon, they're in some sense what could be called complementary, in the sense that the value of them together exceeds the value of the sum of each of the individual items. So if you just have tea, and if you just have lemon by themselves, the sum of the two values, if you just have lemon, lemon is not that useful by itself. You usually use lemon with something else. You usually also have tea with something. Either you have tea with milk, or you have tea with lemon, or you have tea with something. But if you have tea and lemon together, the value of tea and lemon is probably greater than the value of them together. Now this type of property, the substitutive property, of coffee and tea versus the complementarity property of tea and lemon are not at all expressed by this graph. So it seems like it's a property that perhaps is fundamental, and I'm going to argue is fundamental, that's not at all captured by the graph, and so therefore the graph has not really satisfied, is not really doing all that it ideally should be doing for us. So here's another example of, again, 3 real-world, very widely known objects, a hamburger, fries, and Coke. And let's consider 2 different ways of decomposing maybe costs. Now, instead of the value of these 3 items, let's say we're interested in modeling or representing the costs of these 3 items together. And so here are 3 possible example graphical model ways of describing the costs. So in each case, we're interested in a model for the costs of these 3 items together. Okay, and so in the first case, we've got 3 independent or 3 completely separate variables, the hamburger, fries, and Cokes, and so the costs are just the sum of each item individually. In this particular case, we've got a Markov chain, and so in this here we've got that the costs of the hamburger and fries and the soda is equal to 2 terms, each of which consists of a pairwise costs, namely here it's hamburgers and fries, and here it's fries and soda. And then the last case where you have basically a clique over all 3 items. And so any model, and this is really saying nothing. It basically says the costs of these 3 items is equal to some function of the 3 items. And so of course you can do everything here, but there's a limited amount of nuance that one can get, I'm going to argue in the next slide, from these sort of graphical forms of decomposition. And so what we want is a more nuanced way of decomposing functions over objects. And that's where submodularity comes into play. So what does submodularity do? So again, we've got these 3 objects, hamburgers, fries, and a soda. And we want essentially a form of decomposition of the costs in terms of consumer costs, which is when you go to McDonald's and you buy these things, how much do they cost to you as the consumer? But also there's societal costs, and we're going to use as societal costs maybe healthcare costs. How much does it cost society, maybe because of additional costs to the healthcare system, by you eating at McDonald's? And so we have an additive decomposition, so far each term of which involves all 3 of the items, hamburgers, fries, and sodas. Now I'd like to argue that the consumer costs have a property of this form. And this is essentially what could be known as maybe McDonald's Happy Meal. Now what does McDonald's Happy Meal mean? It means that if you consider the costs of a Coke on top of buying just a hamburger, that additional cost of a Coke is greater than the cost of a Coke on top of buying both a fries and hamburger. All right, so oftentimes, in fact, once you buy fries and a hamburger, they'll throw in a Coke for free, right, so that this right-hand side is 0. So this is perhaps a good property that describes the consumer costs of these 3 items. On the other hand, let's consider healthcare costs. So in this particular case, we seem, arguably, to have the opposite phenomenon, which is that from the perspective of individual health, and therefore the corresponding costs to society in people consuming these food items, it's probably the case that the cost of a Coke on top of buying a hamburger and fries is more than the cost of a Coke on top of a hamburger. And in fact, this is just based on an article I found recently in the Journal of Obesity that said that if you substitute starch calories with sugar calories, or you add sugar calories on top of starch calories, then those additional calories of a different form are much worse for your health than it would be the case if you were to, say, consume the sugar calories on top of a food item that's not as starchy. So this is actually based in some recent research about health of items. So it seems like consumer costs have this property, health costs have this property. When you were to, if you look at either of these forms of either of these terms in this additive decomposition, a graphical form of decomposition does not help us. A graphical form doesn't tell us either this nor this. And in fact, in each of these cases, each of these terms in this additive decomposition here can't be sort of further broken down, any further decomposed any further other than these 2 properties. So therefore, again, the graphical decompositions have failed us here, whereas this other form of decomposition has. Now, as it turns out, this function here is a submodular function, And this function here is the supermodular function. And so it seems like by being able to decompose a function in terms of its submodular and supermodular components, maybe that gives us some additional flexibility and power that wasn't possible before with the graphical decomposition. So the question then next becomes, well, what is a submodular function? So a submodular function is a set function. So we're starting with a finite set of objects. And here's a large set of objects, which is represented by this set V. Okay? And we're defining a function on all possible subsets of this set V. And this function evaluates all possible subsets. So for example, it might be the case that we evaluate all of these objects as value 6. Whereas if we were to take a subset of objects, like for example, all of the sushi objects, maybe we give all of the sushi objects, despite their number, the value 1. And maybe if we ask for the value of a diversity of objects, like a piece of sushi and a tree and one of each different type of object, we might evaluate that subset as, say, 6 again, which is the value of the whole set. So a submodular function then is a set function that satisfies certain properties. And the properties can equivalently be written as either this inequality, which basically says that for any A and B, which are subsets of V, it has to be the case that the valuations satisfy f of A plus f of B is greater than or equal to the f of the union plus f of the intersection. Or alternatively, and equivalently, submodularity satisfies what's known as the diminishing returns property, which a lot of people find much more intuitively appealing, because it basically says that the value of what you don't have, let's say that V is some item that you don't have here. This is V over here. V is something that you don't have. The value of what you don't have basically decreases as you get more other stuff. So let's say you start with A, with set A. You don't have V, and so this is the increase in value in gaining V over A. And so that's greater than the increase in value of V over B, where it's the case that B is a superset of A. So this is the idea of diminishing returns. What you don't have becomes less valuable as you get more stuff. And this seems to sort of be a natural model for many of the phenomena in nature and economics and business and values of friendships and Facebook friends and so on and so forth. And in fact, it turns out to be that this seems to be a fairly ubiquitous phenomena in many natural systems, as I've discovered. So now, set functions in general, you can think of them as Boolean functions, or at least a kind of Boolean functions. They're really pseudo-Boolean functions. So a Boolean function is a function on a subset of items, or equivalently a binary vector, where a binary vector can be seen as an indicator function of the subset, where if it's a member of the subset, the corresponding bit is a 1, and if it's not a member of the subset, the corresponding bit is a 0. And a Boolean function is one that then for each, it's essentially a set of logic clauses that returns either a 0, 1 in response to a binary vector. A submodular function is not restricted to return 0, 1. It's not restricted to be 0, 1 valued. It can return any real number. So therefore, a submodular function is a subset of the class of pseudo-Boolean functions. And because of this equivalency, we can define submodularity either on subsets or on bit vectors. And we can go back and forth. And we will be going back and forth a bit in this talk. So if I, for example, write the argument of a function as x, that's just one of A. Basically, that's the bit vector, which is the characterization of this particular subset A. And so we should be able to quickly go back and forth. There's no real difference. So here's another description of a submodular function. I always say this, like all good concepts in computer science, it can be defined using balls and urns. And if it can't be defined using balls and urns, it's not a good concept in computer science. And so here's a submodular function in terms of balls and urns. So the value of an urn is basically the number of distinct colors of balls in the urn, in this case. So on the left-hand side, we've got an urn that starts out with value 2, because there are 2 colors in this urn, red and green. And if you throw in another blue ball, you're increasing the value by 1 because you're increasing the diversity, increasing the number of different colors of balls in that urn. Whereas on the right-hand side, the value starts out with 3, and there's already a blue ball in the urn. But if you throw in an additional blue ball, in fact, no matter how many additional blue balls or red balls or green balls or colors of balls that are already present in the urn that you throw in, you're not going to increase the value at all. So this is a submodular function. The number and submodularity, as I will argue in a second, are therefore great models for diversity in finite data sets or over sets of objects. So just another slight different definition. So the notion of a supermodular function is one where the inequality is switched. So in this case, let's just use the second definition. A supermodular function is known as an improving returns or an increasing returns function, which is that the value of what you don't have increases as you get more stuff. And now there are many things that we find that also satisfy the supermodular relationship. Like, for example, a telephone. A telephone is useless if only one person has a telephone, but as more and more people start having telephones, the telephone becomes larger and larger, or becomes more and more useful and more valuable, thanks to what are called network effects or network externalities. And Facebook is another example, or most apps, like social network apps. Any of these apps like social collaborative driving directions like Waze. These are all the instances of supermodular functions when you measure the value as a function of the number of users that use this thing. And then I also want to briefly mention what a modular function is. So a function that's both submodular and supermodular is known as a modular function. And any modular function can be represented in the following way, where the value of a set of items A is basically equal to some constant, which is often 0, plus a sum of singleton values of the items inside of A. So that function is both submodular and supermodular, and all such functions that are both submodular and supermodular have this property. Okay, with regard to this decomposition property that I mentioned before, it turns out that any function, h, can be decomposed in this way. It can be additively decomposed in terms of a sum of a submodular and a supermodular function. And this is irregardless of any sort of graphical structure. So it seems like, and part of the research that we've been concentrating on a lot recently is, first of all, when is it the case that problems are naturally either submodular, or problems are naturally either supermodular, or when they're not naturally submodular nor supermodular, when can they be naturally decomposed in this way? And moreover, when is the case that such a decomposition can be exploited in some way usefully? Because unlike graphical models, which gives you computational tractability only when the graphical model is in some sense heavily restricted based on, say, things like tree width, a submodular function need not have any form of tree width restriction. You need not have any local interaction with the submodular function. Submodular functions are global functions. They can operate over the entire set of items rather than only locally based on neighborhoods. And so there is no notion of neighborhoods. And so for this reason, I think of graphical models as, I think of submodular functions as like anti-graphical models. They're like, in some sense, the opposite, in the sense that they give us a very different way of doing decomposition. So I think I've already said this. Right, in some cases, it's a more natural decomposition than graphical decomposition. So now, the question, of course, like I said, is, well, suppose you, say, do these decomposition, and maybe either f or g or, are 0. What good does that buy you other than the fact that it gives you a global potential function? Because oftentimes we know that in a graphical model, when it's not tree width restricted, the complexity of dealing with such a model is exponential in that tree width. Or you need to approximate, and oftentimes the approximation guarantees you get in that case are unboundedly poor. So submodularity, in some sense, solves that problem because ordinarily, like let's say you wanted to do some sort of minimization or maximization problem like one of these. There's an exponential number of subsets of a given set. And as the size of the set V gets larger, it grows, to get any kind of quality guarantee, you would need to search over 2 to the n, where n is the number of size of items in V. You'd need to search over 2 to the n possible scores, in some sense, to get any kind of guarantee. But when the function is submodular, on the other hand, this minimization problem here can be done in polynomial time, often lower order polynomial time. Now this is actually an amazing property because a submodular function, it can be shown, has 2 to the n degrees of freedom. So it's not like the function lives in some lower order manifold. And the reason why you can do polynomial time minimization over an exponential size space is because you're really just searching over some low order polynomial size manifold. In fact, a submodular function does truly have 2 to the n degrees of freedom. But it means that you can solve this in polynomial time, which means that there must be an exponential number of possible valuations of the submodular function that you're ignoring, and you still have guarantees of minimality. So that is remarkable. Now, the other thing that is true is the maximization problem on the right-hand side. So this is also something that is, I should mention that minimization, we know that we can minimize convex functions easily. We can't maximize convex functions. But unlike convex functions, a submodular function is such that you can actually maximize it. Not exactly, but approximately in polynomial time, and with a constant factor approximation guarantee. So it turns out that maximizing submodular functions is NP hard, but NP hard is not a showstopper. NP hard is basically say, well, what kind of NP hard is it? In this particular case, it turns out that there's a constant factor, a low order constant factor approximation guarantee for maximizing submodular functions, which, irregardless of the size of the problem that you have. It looks like there's a question there.
Is there a difference between a negative submodular function and a supermodular function? So can you just negate a supermodular function and end up with a submodular one?
Yeah, so it turns out that you can, if you have a submodular function, you can negate it. But oftentimes, a lot of these guarantees are based on things like, for example, the non-negativity of the function. So if you did unconstrained minimization and unconstrained maximization, and say that you do an unconstrained minimization, so if you minimize a submodular function and the function is positive and you negate it, that means that you can do unconstrained supermodular maximization in polynomial time. But what we're going to be doing very quickly, is adding additional constraints, which sort of renders those kinds of flips not applicable any longer. So like, for example, in this slide, most of the time for applications, we want not necessarily to minimize or maximize over all possible subsets, but we care about combinatorial constraints. Now, one of the simplest form of combinatorial constraint is a bounded size. So let's say that S is a constraint set, which are the feasible sets of things that we want to optimize over. And so maybe we care about S's that are no bigger than our budget, which is our size budget K. Or maybe we have some additional modular cost function W, and we care about S's that are no more costly than budget B. Or equivalently, or alternatively, maybe we care about a feasible sets that are combinatorial objects, like, and this is sort of meant to represent combinatorial objects, like maybe the items that we're optimizing over correspond to edges over a graph. So like V are the edges of some graph which have nothing to do with the submodular function, but they're just edges of a graph. And we only care about solutions that are maybe matchings or spanning trees or cuts or edge covers or vertex covers or something. We care about combinatorial objects, but we have essentially a cost, a non-modular cost associated with any one of these combinatorial objects. And we want to, say, minimize or maximize the submodular function subject to it being one of these combinatorial objects. Or there's another really interesting class of combinatorial constraints, which are matroids, which I don't have a chance to get into. But matroids are extraordinarily powerful combinatorial objects that can also be seen as defining feasible sets for those things that we wish to optimize over. Or even more powerfully, I mean, we could ask for the feasible sets to be sublevel or superlevel sets of some other function, which is maybe submodular. So like, we only care about sets S such that its valuation based on some other submodular function is no greater than alpha. So all those problems, it turns out, if it's the case that you know nothing about F, all these problems are easily provably exponential cost, regardless of the P is equal to P NP question. So these are not even NP hard problems. These are just exponential problems. And so you could prove P is equal to NP tomorrow, and you wouldn't help with these problems in the general case. But it turns out, and this is a lot of the work that we've been working on over the past, well, we and many others, I should say, have been working on over the past decade, which is essentially ways of doing these kinds of optimization problems subject to various different constraints. And it turns out that most of them that we found are approximable in some ways. And actually, the approximation algorithms are usually scalable to large problem sizes, and they're fairly simple, and they work well in practice. So then the next critique you might have is, well, are submodular functions limited? Is it a very small family of functions, the submodular functions? And so therefore, I won't find one within your set of submodular functions that's useful for my problem. So it turns out that is not true. So the first thing to note is that the entropy function itself is a submodular function. So the entropy function, raise your hand if you know what the entropy function is. Okay, good. So the entropy function, now here we're not talking about the entropy function as a function of the probability distribution that's governing the random variables. We're thinking of the entropy function as a function of the subset of random variables over which we're measuring the entropy. So we're thinking of it as A, and A is an index of random variables, and the entropy function is defined as computing the entropy over that subset of random variables. Now this turns out to be a submodular function. And in fact, this was noted back in Shannon's 1948 paper that talked about the subadditivity. And he mentioned the subadditivity of the entropy function, but it wasn't really until McGill in 1954. This is actually an interesting anecdotal piece of information, which is that McGill stated that further conditioning reduces entropy, which is this inequality here. And he attributed it to Shannon, but Shannon didn't say it, so as far as I can tell. So the question is, who first noted the submodularity of entropy? So McGill said Shannon did it, and Shannon didn't claim it, so who knows. But this is identical. This condition here is identical to submodularity in the case of entropy. But there are many other submodular functions as well. And a large part of the work in using submodularity in machine learning is how do you choose the right function? Just like when you're using a graphical model in a machine learning problem, how do you choose the right graphical model? And once you've chosen the right graphical model, how do you identify the parameters? Or in a deep model, how do you choose the structure or the topology of the deep model, and how do you choose those parameters? Deep models are a very large class of functions. Graphical models are a very large class of functions. Submodularity are a very, very large class of functions. And so this basically opens the doors to all kinds of research opportunities for how do you choose the submodular function. And this has also been something that's been occupying a lot of our time. Now, the question is, it doesn't matter how you choose the submodular function. If you maximize the submodular function, submodular functions are very sort of good models of diversity or coverage or span, or maybe what could be called irredundancy or information, right? Like you want to maximize the information. You want to choose a subset of items that are large. That basically means that you want to choose a subset of items that have a lot of information, which is actually exactly the way that we've approached summarization problems. Because if a submodular function is an information function, we want to choose a small subset that has lots of information. That should be the condition that defines what a good summary is. On the other hand, when you want to minimize submodular functions, typically it's the case that submodularity is a useful model for things like interactive costs or cooperative costs. Costs in the sense that the two items together maybe cost less than they would if you were to consider them in isolation. And there's a lot of instances of that historically in economics and operations research. But other kinds of things are like complexity and roughness and irregularity. All of those are sort of well modeled by instances of submodular functions. So I promised that I would talk a little bit about some of the applications, and that I also promised that this was a high-level talk. And so far, this is pretty high level. But I wanted to give a pause before I start talking about the applications to give people an opportunity to ask some questions now, because now we're going to sort of move into the application section of the talk. Everyone understands everything 100%. Is that correct? Raise your hand if you understood everything 100%. OK, so if you didn't raise your hand, could you please ask a question? This is supposed to be a class, right? So I have to force people to ask questions.
Well, the 100% business seemed like you were trying to sandbag us somehow with some question that was about to follow.
Oh, no.
So
I'm not that clear.
But your explanation was very clear.
OK, so well, if there are any questions, then please ask. And it doesn't have to be 100%. It could be like 96.3%, which I'm borrowing your joke. So, OK, well, if there's no questions, then you can still ask questions at the next slide. OK, so what is summarization? So I think that, this is getting to the problem of data science. And I've said this to some of you many times before. There's sort of what data science seems to be traditionally being approached in two ways. One is the people who've been working on parallel computing systems are very happy because suddenly, especially since microprocessor performance isn't getting faster anymore, people who are working on parallel computing and have data science are very happy because you have the need for parallel computing and an easy way to do parallelization, which is how do you split the data across, which is splitting the data across multiple processors. So parallel computing and computing systems is one front in the data science field of data science. Another front is statistics, which is now you've got large data, you can produce more reliable and more robust and estimates, statistical estimates. And so data science is great for statistics. But there's another issue of data science which I don't think is being addressed as strongly as these first two, and that's essentially the issue of redundancy in data, which is that people are piling on massive amounts of data into Pile and saying, this is great, I've got this massive data set. This is so much better than before. There's no data like more data, it has been said many times. But in fact, that may not be true if it's the case that the data set is highly redundant. And most data sets, I would argue, are collected somewhat indiscriminately in the sense that there isn't a coordination effort at the data collection time to ensure that each new piece of data item that they throw onto this big pile of data is novel and represents something new. And so what that ends up doing is it means that the people who are working on parallel computing might be getting 100% machine efficiency, but in fact they're not getting 100% information efficiency because the machine's working, they're getting their 14 teraflops on their GPU machines, but the problem is that they're essentially doing redundant computations because the data itself is redundant. And so the idea of summarization, which is what I think submodular functions address, is the idea of taking data sets and reducing it to its core, to its irredundant, essential set of elements from which you can essentially infer the same stuff, but with much less computation, and thereby achieve this idea of information efficiency. So that's the idea. Okay. Now, the first thing we approach this with is actually, well, first of all, why are submodular functions useful for doing this problem? So I said before that submodular functions are very good models of information. So the entropy function, obviously, is a very good function that represents information. It basically corresponds to the limits of compressibility of a random source governed by that probability distribution. And so therefore, the limits of compressibility, in some sense, can represent the information in that source. It's the number of bits below which you're guaranteed to get some kind of distortion. It turns out that all submodular functions have this property of being ideal for representing information in data sets, but you don't need to have a probability distribution over the data. And we can define notions of things like combinatorial independence. So A is independent of B, or A is combinatorially independent of B, if it's the case that A and B are additive at their intersection. So we have this equality. So that's the definition of independence. We also have the definition of conditional independence. It's combinatorially conditionally independent, if it's the case that this equality is true. And in fact, most of the notions of dependence and independence from a statistical perspective are also true from a combinatorial perspective if you define them in this way using a submodular function. And I should also mention that if it is the case that the submodular function was the entropy function, then these would be identical to the notions of statistical independence. You can also define things like sufficient statistics and all sorts of other things using these combinatorial quantities, which is a big generalization over what can be done if one is purely thinking of it statistically. So, so I think because of this, and also because, as Shannon argued back in the 40s, that this property, he didn't say this directly, but the property of submodularity is sort of the ideal property of an information function. We can think of submodularity as being an ideal class of functions to investigate strategies for measuring information in data sets for which there's no underlying probability distribution. So then, armed with this idea, this is a while ago now. We tried to address the problem of document summarization. And document summarization is a really good problem because it's been studied by the natural language processing community for a while. There were standardized benchmarks for it, and there's standard ways of evaluating how good a summary was without actually needing to go out and ask a human again how good a summary is. And so the idea of document summarization, just briefly, is you have a large number of newspaper articles or something that you need to read, but it's redundant, and you want to reduce it to its essential subset, core. And submodularity seems like a good model for document summarization. So the idea here is on the left. You can't really see it that well. The idea is you're considering adding this blue sentence over here. Can you guys see this? Can you see it? Okay, so this is light blue or magenta or something. cyan, I guess is the right color, cyan sentence. Here you have a bunch of sentences, and you're considering adding this sentence to this context versus the same sentence to this larger context because you've got a larger thing. Chances are that that cyan sentence becomes less essential when the context it is considered in grows. Certainly, if you take any article and remove any one sentence from that article, chances are you'll still get the elements, you'll get the essence of that article. And as you keep removing sentences, you still, as long as you don't remove too much, you'll get essentially the main point of what the article is saying. And so it seems like, therefore, submodularity is a good model. So when we looked at this, interestingly enough, we looked in the document summarization community over the preceding decade and found that the people in the NLP community had been using submodular functions for 10 years without realizing they were using submodular functions. And they were setting up a submodular optimization problem and solving it with integer linear programming solvers and complaining about the fact that ILP solvers can't scale to data sets larger than maybe 100, 150. And if they had realized that they were working with submodular functions, they would have realized that they could have used the algorithms associated with submodular functions and they would scale to big data sizes. And that's kind of what we did. Now, the other thing I want to mention is how do you learn? One of the big problems, and we and a number of others have been looking at how do you learn a submodular function. And we've been interested in learning mixtures of submodular functions using a max margin framework. And the basic idea is that there have been some negative results that say if you consider the entire, it's submodular functions live in a space of r to the 2 to the n, right? So it's a 2 to the n dimensional space. And if you try to learn everywhere within this space, it's actually a cone, which is a subset of r to the 2 to the n. And if you learn everywhere within that space, it turns out that learning, and depending on how you just wish to learn, is actually hard. It's actually hard to learn a submodular function. But on the other hand, if you have different learning objectives, like maybe we only wish to learn a submodular function that, when optimized, is good, and maybe also we only wish to learn, say, a mixture of components, and we're only interested in learning the mixture coefficients, then suddenly learning becomes a lot easier, yet at the same time it's still rich and still useful and practical. And so that's exactly what we did here, where we learned in a max margin framework. And we got pretty nice results. So basically this is 2 years of work. It's 2010, 2011, and 2012. This is a while ago now. But each of these results were the state of the art, if I remember correctly, the best results ever reported on this corpora. And then, so this was just basically where we handcrafted the function. Here's where we did a better job handcrafting the function, and here's where we learned the function. And you can see that the results are getting better. Unfortunately, the students stopped. Otherwise, I'm sure the results would have kept going up in that way. By now, we would be much better than humans. Let me just talk a little bit about some of the ideas of what these applications are. So, I mean, speech recognition, as you know, is a problem that I've worked on a lot in the past, and I think it's still a really great instance of a machine learning problem, largely because the data sets are standardized, and they're big, and they're complex, and it's hard to train. And deep models is something that has revolutionized the area of speech recognition. But one of the problems with deep models is that they're also very, very expensive to train. Now, if you combine very, very expensive machine learning methods to train with big redundant data, you get inefficiency. Not necessarily computational inefficiency, but you get informational inefficiency. And so the idea is the following. So we know the old phrase, there's no data like more data. But I think a better phrase is really there's no data like core data, because the core data is the essential data that represents the information that you need to learn something in a machine learning system without having the redundancy that typically exists in data sets. Now, you've probably seen these kinds of learning curves before. So this is actually one taken from Andrew Ng's Stanford machine learning class, which this is showing various different machine learning methods and how does the accuracy grow as a function of the training set size. Now, there's two reasons why you see these leveling off properties in learning curves. One is that the model capacity itself, if you're using a parametric model, a model whose complexity doesn't grow the size of the data, the model itself eventually saturates, and there's not much more a model can learn. But something else that is not nearly as much studied is the fact that that the data itself is redundant. And if you get more and more data collected from the same way, the efficiency of what you can learn from the amount of data decreases. And so therefore, the accuracy as a function of the data levels off and stops increasing. And this is something, if you look around the web, you see that this is ubiquitous, that this kind of problem of leveling off in a variety of different settings, in a variety of different problems for speech and for natural language processing and for image processing and for many, many other problems in machine learning, you tend to always have this kind of property, this leveling off. Now, it turns out that this is like a concave function, right? In each of these cases, it's like a noisy concave function. It turns out that if this property is true for any permutation of the data, then the function is submodular. So what this tends to suggest is that the accuracy function as a function of the training data set is probably well modeled by a submodular function. And if it's well modeled by a submodular function, we can then choose subsets using submodular optimization methods if we can find a representative submodular function that's a good model, and therefore train machine learning systems much more efficiently. So I'm going to skip a lot of stuff and get to some results. So we tried this on speech. This is on a well-known corpus, large vocabulary, considered a fairly reasonably respectable corpus in the speech recognition domain. It's called Switchboard. And this is looking at the submodular method on a Gaussian mixture system on the above and a deep model system below. And this is all of the data on the right-hand column. And this is various different subsets of the data. And what's interesting is that the performance of a deep system with only 5% of the training data is essentially the same as a Gaussian system with all of the data. So if you're interested in, say, doing development, like you don't know the topology of your deep system or something, you want to try some experiments, maybe you should choose a good 5% of the data, and it would allow you to, your experimental turnaround time to be much less than it would be if you were to, say, doing development on all of the data. That doesn't mean that you don't ever use all of the data in this particular case. It means that there must be some information in all of the data still. But if you're doing development, this is actually a useful result, and so you should be able to get to a good system more quickly. I'm out of time, but I want to tell you about a project that we're just beginning to work on, which I think is kind of fun, and it uses submodularity. Has anyone ever submitted papers to conferences? Has anyone ever been unhappy with the quality of the reviews? Raise your hand if you've been unhappy. Okay, raise your hand if you've never been unhappy. Okay, so nobody's never been unhappy. So you have essentially a set of papers that need reviews, okay, in a conference, and you have a bunch of reviewers, okay? Now, what you want to do is you want to match these papers to reviewers. Now, you might set it up initially as a bipartite graph where potentially every paper could be assigned to every reviewer, right? But now, you might say, okay, well, there's a limit on the number of, you want to make sure that every paper has at least 3 reviewers, or maybe exactly 3 reviewers. And you want to make sure that each reviewer has a sort of customized number of possible papers that they're assigned. Like this person maybe doesn't get any reviews assigned to them because that's someone who's known to be not the best reviewer in the world. And so basically, you can assign these numbers. Now, another property is that maybe papers should each have a diversity of reviewers. You know, one of the things that's typical that would be useful that a conference reviewing system would provide that would be useful for a conference is that each paper is assigned an expert in the field and maybe a general purpose, sort of a general overall field expert, and maybe somebody else, and maybe sort of a young graduate student like yourself or something. And the idea is that if every paper is assigned a diversity of reviewers, then that paper would be given a broad perspective evaluation, unlike if everybody was, say, of one particular form. Yet at the same time, reviewers ideally should be given a homogeneous collection of papers to review. So whenever if you've ever reviewed for a conference and you have 8 papers, say from NIPS, and they're all different. So each paper you have to do a separate background reading for, and you spend a lot of time on each one, and then you can't reuse that background reading for all of the other papers because the papers themselves are diverse. But if it was the case instead that the papers were homogeneous, then given a fixed amount of time, you as a reviewer would be able to do a much better job reviewing the papers from a technical perspective, and you'd be able to calibrate better because you would be able to have a localized ranked list of the papers, all, say, on support vector machines, or whatever the area it is that you're reviewing on. So it turns out that this problem turns out to be a submodular optimization problem. And so one of the things we're working on right now is we're developing a system. This is actually something I'm doing with Andrew McCallum. We're developing a system that uses a submodular optimization system to have a new system that hopefully will replace the Toronto paper matching system to do a much better job assigning papers to reviewers. And there's a lot of other things as well. So I want to end. There's a lot of other stuff like parallel computing, a lot of other applications, but I am obviously not calibrated for a 1-hour talk either. So I just want to say that there are many, many definitions of submodular functions. These are, each one of these equations being true would equivalently define a submodular function. Over the past 100 years, submodularity has been repeatedly and independently discovered many times, each time with a different name. You might find submodular functions called submodular, attractive, associative, regular, ferromagnetic, POTS, subadditive, strongly subadditive, quasi-antitune, two-antitune, convex, upper semi-modular, Monge, Fisher-Hadamard, subvaluations, beta, ground set rank, competitiveness, or negative synergy. So all of those things have been used to define submodularity. So what I like to think of is to go back to Henri Poincaré, and that's my feeble attempt at French. But basically, he said that mathematics is the art of giving the same name to different things. But that apparently was in response to an anonymous poet who said that poetry is the art of giving different names to the same thing. So based on this, I think we can arguably say that submodular functions are a form of poetry. So anyway, that's it. I'd like to acknowledge this is my group. This is us drinking beer and talking about submodularity. So thanks very much. That's the end. Any questions? Yeah.
So I know with typical continuous optimization problems, you might choose a loss function that's convex because that is tractable for typical optimization strategies. But in fact, the performance measure that matters out in the domain is something that's slightly different than that loss function. So you have a little bit of disconnect, and you kind of have to take your lumps however that works out. Are there comparable things that go on with submodular optimization where you make a nice submodular formulation because then it's tractable for your optimization algorithm, but in fact the domain is something different from that?
Yeah. There's many ways that that's true. So first of all, I mean, when you look at all of the recent work on stochastic gradient-based methods and like Hogwild and Buckwild and those sorts of things that on parallel computing, those things are all basically analyzed mathematically from the perspective of convex functions. But then when you try them to non-convex functions, they just kind of work, right? And so from an analysis vehicle, you might have an algorithm, a discrete algorithm that was developed for submodular functions that just for some reason works on non-submodular functions. But it turns out that also, even more so, there are actually ways of measuring distance from submodularity. So there's like 3 different ways that you can actually measure distance from submodularity. And in some of those cases, you can show that depending on the degree to which the function is close to the class of submodular functions corresponds also to the approximation guarantee you get. And then there's a third answer to that question, which is that oftentimes, even when your problem is not submodular, you can decompose it. The whole idea of this decomposition, this submodular decomposition, is that h, any function h can be represented as a submodular plus a supermodular function. It's just by that fact that you can do that decomposition, if you can find that decomposition, that suddenly opens the doors to all kinds of different algorithms that usually behave very nicely in practice, we found. So studying submodular optimization doesn't mean you're forced to insist that everything in the world is submodular. It just gives you avenues to pursue algorithms for solving your non-submodular problems, just in the same way that studying convexity doesn't force you to assume that your problems are all convex. So it's exactly analogous. So yes, that's exactly right. Yeah.
What are the connections between submodularity and clustering?
Well, you can define, clustering is basically the idea of taking data and grouping it into groups. Now you can define, there's an innumerable number of different clustering procedures, many of which can be defined using submodular functions. Like, for example, one way of doing a clustering is to define the submodular mutual information function and then partition the set and recursively partition the set, and you get clusters, each cluster of which is homogeneous from the perspective of the submodular function. So just by instantiating it with a submodular function, you've now defined a whole family of different submodular functions. And if you define it with there's a function called like k-mutoids clustering algorithm, for example, can be defined using the facility location submodular function. You would get different clustering algorithms. But clustering is also quite different as well, because you can define clustering objectives and algorithms out of the context of submodularity, of course. But there's quite a bit of overlap. Yeah.
When you're learning, or when you're dealing with like problems and you're using submodular functions to model something, for the most part, are you learning these functions, or are you constructing them and then minimizing them?
That's a great question. So, I mean, this is part of the research challenge, right? Because, you know, it's one thing to say, okay, there's this vast family of submodular functions, and if you choose the right one, you can do great. Like, for example, the accuracy function for machine learning subset selection, right? So you see all these curves, and you say, okay, it's probably approximately submodular. But how do you find that one? How do you produce that one? So one way, and we've done this, and many other people have done this, is you say you handcraft one. You say, well, I think it's a little bit of this, and a little bit of this, and a little bit of this, and maybe you have some hyperparameters, and you do a grid search or some sort of null-dermeed search over a development set on the hyperparameters. But a much more compelling and interesting and much more open problem is how do you define subclasses of submodular functions over which you can learn in some way that assures that you get the best instance of a submodular function within that subclass. So these are open problems, but they're partially. I mean, there are some solutions so that you can actually use them in practice now. But I see that as a big open area for the future. I should mention again. I mentioned this at the beginning of the talk. So I'm teaching a class on submodular functions starting in spring. So if you want to learn about all of the details, or at least some of the details, because even in one 10-week class, we can't fully explore. It takes a while. It takes some investment of time to sort of get a strong intuition. And I've tried to distill in this talk some of the intuitions that I've gained over the years by studying these things. But it takes a while, just like in convexity, it takes a while to get an intuition for what's going on there. But I think it's well worth the investment, and it seems to be a forthcoming area within machine learning and artificial intelligence. And so I would recommend taking the class.
You should probably take questions offline at this point, but thanks very much.